In this project, I am using a simple LiDAR apparatus to scan and collect data about a particular target on the University of Maryland campus. This data will be processed to create a 3D point cloud of the target. This is the final project for the ENME 489Y remote sensing class. My target is the statue of Mary at the Catholic Student Center. I chose this target because I thought it would be something more unique that other students wouldn't pick, and as a Catholic myself, it has more personal meaning than other targets across campus. The target is white in color with a matte finish and relatively complicated geometry. There is also no access to the backside of the statue. Remote sensing is the science of obtaining information about a target without having a sensor in direct physical contact with the target, including things such as radar, LiDAR, sonar, and more. Passive remote sensing simply uses naturally occurring radiation such as sunlight in the sensing process. Active remote sensing uses self-generated radiation. LiDAR is light detection and ranging, where light is transmitted into an environment, backscattered by a target, and then detected and received by analyzers. Measuring the time it takes for the light to travel to and from the target provides the ranging information. Computer vision is where computers are enabled to identify and process images and provide useful outputs similar to how humans see. For this project, we will use an active sensing LiDAR apparatus to collect data about a target and use computer vision to help process the data and create a 3D point cloud. The LiDAR apparatus contains several important components. All the components are integrated using the 3D printed chassis. The transmitter for the sensor is the line laser located at the bottom of the chassis. The receiver is the camera located at the other end of the chassis. The Arduino is used to power the line laser, and the Raspberry Pi is connected to the camera and used for data collection. The old smartphone is used to collect IMU angle information, and all components are powered by a battery pack, and the apparatus is connected to a tripod. It is important to properly calibrate the LiDAR so that reasonably accurate ranging data can be collected. Calibration tests started with a single point laser and then moved on to using the actual line laser on the apparatus. Both calibration tests yielded acceptable results when compared to the theoretical curves. The only change I had to make was for the radian offset value for the LiDAR apparatus, where I changed it to 0.007. As you can see, the target of interest is here in front of me. It's a pretty complex geometry, but should be relatively easy to pick up because of the light coloration of the statue. LiDAR here set up, a laser, iPhone to give us the IMU angle, and camera to pick up the data. Moving back, we will close out the light, read the IMU angle of 16 degrees. Now run our code. Entering 16 degrees. Waiting for data to be collected. And there we have the image. Overall, I did not encounter too many problems with this project. There were no outlets near my target, so I had to switch from my laptop to my cell phone after a while. Luckily, there is a VNC viewer app that worked just fine. In some cases with passing cars, the images I collected would be a bit brighter from the headlights, but I worked on using an HSV mask that would still work with them.
Here we are again doing some data processing with the images taken during the project target scan. As you can see, we have a series of images with the associated IMU angle printed in the corner. This is just one of the views I took. I took some from my left-hand side and right-hand side as well as the front of the target. First thing we're going to want to do is run colorpicker.py to get a good HSV value. So we'll again play with the sliders and filter out as much of the extraneous stuff as possible. And end up getting something along these lines. As you can see, we still have some data that will show up as noise, but we still have all of the laser image for the most part. So moving over to data generation.py, we're going to do this several times for all the different views, one for each view, and it's going to output the test results again as x, y, and z coordinates. And once we have those coordinates, we move over to the MATLAB code. And so in MATLAB, we import each of the 3 documents from the 3 different sides taken. And this part is important here is the transformation matrix that will rotate the point cloud of the different sides so we can get them in the correct orientation. And here you see I rotated 90 degrees. So we extract the x, y, and z for each side, and then we perform the transforms by multiplying our x, y, and z data by the transformation matrix. And then you also have to, depending on your point cloud, add a translation value, and this moves it into place so it fits together with the other data. And also another transformation for the left side. And then when you run this together, you can see the 3 different angles that'll be plotted together, and they'll be in different colors so we can discern which side is which. And then we'll be able to get a comparison here once we get the new image. This is an image of the original picture, and once MATLAB finishes processing, we'll be able to compare the data clouds. As I mentioned in the earlier video, there's limitation with this target because I can only get around the front and sides, and so the back is incomplete. Alright, so now with the data cloud provided here, we can take a look at what we have. You can see we have the green represents my right hand side, the red my left hand side, and the blue the front. And you can see it turned out a pretty decent scan. When you look at the profile and even the front, you can see some of the crown. You can see the crown on the baby as well as the baby. You can see the different folds of fabric, and all in all, a pretty decent point cloud. Starting with the data collected from MATLAB, we put all of the different views of the target from the scans into one file in Excel and exported it as a text file so we could import it into the MeshLab program. Once inside MeshLab, we go ahead and open up a file with all the data for the point cloud in it. And once we open the data, we'll see a point cloud that looks very similar to what we had before in MATLAB. We're going to have it separated by spaces. And you can see it imports the point cloud. Before we make the mesh, one thing we're going to want to do is trim out all of this noise as best as possible. So we'll select all the points we don't want and get rid of them. Once the point cloud is cleaned up as much as possible, we'll go ahead and alter the normals for each of the points. And for now, I think we'll stick with the neighbor number of 10 and apply that. Once we have that set, we can go ahead and add our mesh. So we'll have to alter these values some to get a good mesh. Found that once you have this set up, you can go ahead and trim away excess faces. And going back to where I was working earlier, I managed to get a point cloud or a mesh like this. It's not the best, but you can still make out some of the point cloud, some of the target it's supposed to be. You can see the head and body of the infant.